All right, so we're going to go through two examples to wrap up 8-1. The directions for this first one ask us to find the local extrema and point of inflection for the given function. And the function that we are given is x times e raised to the negative x power. Okay, so our first step with this, anytime we are finding local extrema or points of inflection, we want our first step to be to find the domain of the function that we are given. And I think it's probably best for us to rewrite this function as x divided by e raised to the x power as far as checking domain is concerned. Because with that function being rational, we know that that function is undefined only when our denominator is 0, and our denominator e raised to the x power cannot be equal to 0. Okay, so the domain of this is all real numbers. Okay, so when it comes to differentiating, it does not matter if we differentiate x times e raised to the negative x power or x over e raised to the x power. The first one using product rule, the second one using quotient rule. You're going to get the same thing either way. I'm going to take the highlighted function in yellow and differentiate it because I think we probably have a little less practice working with that. So I'm going to use product rule to differentiate here, which is the derivative of the first, which is 1, times the second, e raised to the negative x power, plus the first function x, times the derivative of the second, which is e raised to the negative x power, times the derivative of the exponent, which is negative 1. Okay, so if I want to simplify this derivative, I can factor out e raised to the negative x power. When I do so, that gives me 1 minus x. Now, it may be easier, because we know we're going to have to find critical points for this. It may be easier for us to write this as a quotient to determine critical points. If we do that, we get 1 minus x over e raised to the x power. So critical points are going to be where the derivative is 0, and that happens when the numerator is 0 at x is equal to 1. It's also where the derivative is undefined, which happens when the denominator is 0, but that denominator is never going to be 0. Okay, and in fact, that denominator is always going to be positive. Okay, so when I put that critical point then on my number line for f prime of x, if I pick a value smaller than 1, let's say I pick 0, the numerator will be 1 minus 0, which is positive. The denominator is always positive, so the resulting quotient is going to be positive. If I pick a value bigger than 1, say I pick 2, numerator is negative, denominator is positive, the resulting quotient is negative. Okay, so because the derivative changes sign from positive to negative, we know we have a local max at x coordinate of our point is 1. And then when I plug 1 into the original function, we get 1 times e to the negative 1 power, which is 1 over e. Okay, so that is our local max. Now, I'm going to do one more thing before we determine point of inflection. We know to find a point of inflection, we need to find the domain of the derivative f prime. Okay, and the domain of the derivative f prime is going to be all real numbers. There are no values for which that denominator is going to be equal to 0. Okay, so anytime that whenever I check f double prime and the concavity changes, that means that that is going to be a point of inflection for me. So again, we have the ability to differentiate this f prime in yellow or this f prime in blue to find f double prime. I'm going to take the f prime in yellow to differentiate. Okay, so using product rule, that's going to be the derivative of the first which is e to the negative x times negative 1. So I'm going to just put that factor of negative 1 out front, times the second, 1 minus x, plus the first, e to the negative x power, times the derivative of the second, which is going to be negative 1. And then for f double prime, I can factor out negative e raised to the negative x power, and that leaves me with 1 minus x plus 1, which makes f double prime of x equal to negative e to the negative x power times 2 minus x. If I want to write that in fraction form, that will be 2 minus x over the opposite of opposite of e to the x power. Okay, so my critical points here are going to be where the second derivative is equal to 0, which happens at x is equal to 2, or when the second derivative is undefined, and that second derivative is never going to be undefined because our denominator is never going to be equal to 0. Okay, so we make ourselves a sign chart for f double prime. We put 2 on. If I pick a value smaller than 2, let's say I pick 0, we're going to get 2 minus 0, which we're taking the opposite of. So that's negative 2 over e to the 0 power, which is 1, and negative 2 over 1 is negative 2. Okay, so that's going to be negative. And if I pick a value bigger than 2, let's say I pick 3, we get 2 minus 3, which is negative 1, which we're taking the opposite of, which is 1, over e cubed. So we have a positive divided by a positive. So that resulting quotient is going to be positive. Okay, so we have a point of inflection at the x coordinate of our point is 2, and then the y coordinate of my point I get by plugging 2 into my original function. And we get 2 times e to the negative 2 power, which is 2 over e squared. Okay, so let's move on to the next one. Next one, directions ask us to find the equation of the line tangent to the curve e raised to the x squared times y power is equal to x plus y at the point 0, 1. Okay, I want you guys to try that one, and then once you're done, unpause the video, and then I'll work through the problem with you guys. Okay, so first thing we need to do with this one is we need to check and see if the point that we are given, 0, 1, lies on the graph of that curve. So I'm going to plug 0 in for x, 1 in for y, and check and see if I get a true statement. So we get e to the 0 times 1 power, which is e to the 0 power on the left-hand side, equal to 0 plus 1, and e to the 0 power is equal to 1. So that checks out. That is our point of tangency. Okay, so what we need to do here is we need to take the derivative with respect to x of that equation, that implicitly defined equation, using implicit differentiation. Okay, so the derivative of this equation will be the function itself, e raised to the x squared times y power, times the derivative of the exponent, which I have to differentiate using product rule, which is the derivative of the first, 2x, times the second y, plus the first x squared, times the derivative of the second y prime. And that's going to be equal to the derivative of the right-hand side. So the derivative of x on the right-hand side is 1, plus the derivative of y with respect to x on the right-hand side is going to be y prime. Okay, so I want to work to isolate y prime. So I'm going to distribute e to the x squared y power across both of those terms. So that's going to give me 2xy times e to the x squared times y power plus x squared times e to the x squared y power times y prime is equal to 1 plus y prime. Okay, so I'm going to move the y prime terms to the left-hand side, the non-y prime terms to the right-hand side, and then I'm going to factor a y prime out of the left-hand side as well. So when I do that, I get x squared e raised to the x squared y power minus 1 times y prime equal to 1 minus 2xy times e raised to the x squared y power. And then I'm going to isolate y prime. So we get y prime equal to 1 minus 2xy e raised to the x squared y power over x squared times e raised to the x squared y power minus 1. Okay, so all we want to do with this is calculate the value of the derivative by plugging in our point of tangency, the ordered pair 0, 1. Now, the nice thing about this is if we plug 0 in for x, that highlighted factor in the numerator is going to be 0, which makes that entire product 0. So that just leaves me with 1 in the numerator. And when I do the same thing in the denominator, when I plug 0 into that factor of x, then that entire product is going to be equal to 0. So that just leaves me with negative 1 in the denominator. And 1 divided by negative 1 is negative 1. Once I have slope and point, I'm just going to plug that into my point slope formula, which is y minus the y coordinate 1 equal to the slope negative 1 times x minus 0. And that right there is our tangent line equation. Okay, so that is going to wrap up section 8-1 for us.